Hi, we're going to talk about polar coordinates in this lecture and the next lecture. Polar coordinates are just another way to represent points in the coordinate plane. We usually think about the coordinate plane with x and y coordinates. We're going to put different coordinates on the plane, so it's just another way to describe where a point is located in the plane. So before we go through the notes that I sent you, and by the way, we're going to go through about half of these notes during this lecture. In the lecture that I'll post for Monday, we'll go through the last half of the notes. Okay, so before we talk about the notes, let's just talk about points in general. So let's say we have xy coordinates. So if I have a point in the plane, we usually think about xy coordinates for that point. And that, of course, means how far in the x direction did you go? So this distance from here, from the y-axis out to this point, horizontally is x. And for here, that means that this distance vertically from the x-axis up to that point, where that point is vertically, is y. So written another way, I could think about making a right triangle here, and then this side would have length x, and this side would have length y. So that's how we get our points in the plane when we just talk about how far left or right did we go, how far up or down did we go. That's how we get our xy coordinates. But I drew the right triangle here on purpose because there's another way to describe where this point is. So this point, where it is a certain distance away from the origin. Okay? And it's the length of that hypotenuse of that right triangle. So maybe we'll call that r. R for radius. And, well, of course, there's lots of points that have that distance away from the origin, right? If I think about any circle centered at the origin would have that radius, right? So the radius isn't enough to describe it, not how far out are we, but we also have this angle here that's made with the x-axis. This, say I'll call it theta. Once I know how far away we are from the origin, and what angle we make with the positive x-axis, I have another set of coordinates. And that's what we refer to as our polar coordinates. So let's draw that on a separate picture so I don't have so many lines going on. Now on polar coordinates, we really only need the positive x-axis. We don't need the whole thing. We refer to this as the polar axis. And just for argument's sake, for right now, think of this as your positive x-axis. Okay. Well, if this is the positive x-axis, then this would represent the origin, but in polar coordinates, we give it a different name. We refer to this as the pole. Again, this is really what you typically think of as the origin. All right. So if I want to point in polar coordinates, we first describe the r, how far away from the pole are we, and then describe the theta. So in the picture, much like I drew for the picture for the xy coordinates, this distance, the r, represents this distance, and the theta represents this angle. Okay? So that's what we mean by polar coordinates. How far out do you go, and then what angle do you make with the positive x-axis? All right. So from this, we automatically get some conversions between, these are called, okay, so again, these are called polar coordinates. These are typically called rectangular coordinates, or perhaps you might hear them called Cartesian coordinates. It's another word for it, named after Rene Descartes. Yeah, I believe Hawkes refers to them as rectangular, and I believe I refer to them as rectangular in the notes later on. So I'll try to say rectangular, but I might slip and say Cartesian because it means the same thing. All right, we have some conversions automatically just by this right triangle relationship that we've mentioned here. And these conversions are going to be important for the not just for the types of problems that we're going to do, but when you get to calculus, a lot of problems that you do that involve polar coordinates involve being able to recognize forms that are more simply written in polar coordinates than they are in rectangular coordinates. We're going to talk about a little bit about that as we go through this, but we're not going to do it nearly as much as what you need to recognize in calculus. So this is just a precursor. Okay, so let's concentrate on this right triangle. I'm going to redraw it down here. All right, so for this right triangle, we have x, we have y, we have r, we have theta. Again, one of the things that we're going to be interested in with these polar coordinates is being able to convert back and forth, meaning if you are given a set of Cartesian coordinates, can you find the polar coordinates? Given a set of polar coordinates, can you find the, I just said Cartesian, can you find the rectangular coordinates? All right, so there's actually going to be 4 of these conversion formulas that are going to be very, very helpful to us. And any conversion formula basically is going to involve 3 of the variables. So one of them is pretty easy. If I ignore the theta, of course, there's a relationship that's very easy for us that we recognize x and y and r because we have a right triangle. So one of our conversion formulas that we have is x squared plus y squared equals r squared. This is what I mean by, in calculus, being able to recognize forms that are more easily described in polar than they are in rectangular. And notice here, this x squared plus y squared, we can describe with a single variable rather than requiring 2. Okay, so that makes it a little bit easier. And well, like I said, we'll see what we mean by why this is an easier description for a certain type of shape later on. Actually, in the next lecture, we won't talk about it in this particular lecture. All right, well, there's another, let's ignore the r now and have another relationship between the x, the y, and the theta. Well, I see that my theta here is my angle, my y is opposite that angle, and my x is adjacent that angle. So if I do y over x, that has to be tangent of theta. Okay, so these two relationships are very helpful for us from changing from rectangular coordinates. If we're given x and y, we can figure out r from the x and the y, and we can figure out theta from the x and the y. Okay, so these are very helpful for converting from rectangular to polar. All right, I told you there were 4 of these, so let's see if we can figure out what the other 2 are. So these want to go from converting from from polar to rectangular. So again, we're going to do this 3 at a time, ignoring the 4th one. Let's look at r, theta, and x. X is the adjacent side of theta. R is the hypotenuse of the right triangle. So we have adjacent and hypotenuse. That's cosine of theta is x over r, adjacent over hypotenuse. We ordinarily will rewrite this equation as x equals r cosine of theta. Looking at our right triangle again, we can do the same thing. If we ignore the x and just look at the theta, the y, and the r, y is opposite theta, r is still the hypotenuse, so now we have sine of theta is y over r, and again, typically we rewrite that solving it for y, and we have y equals r sine theta. So these conversion formulas are used from converting from polar to rectangular. All right, so let's do some problems. Let's do some problems where we're going to be graphing some polar coordinates. We're going to be converting polar coordinates from rectangular to polar and from polar to rectangular. Okay, and that's what we're going to concentrate on today, doing those kinds of problems. On the lecture for Monday, what we'll be doing is looking at equations and converting equations from polar to rectangular and back. All right, so let's go over to the first page notes here. And this problem asks us to plot some points, even though it doesn't have that written in the directions. It wants us to plot these points. All right, so the way let's first, before we start plotting anything, let's look at this graph paper, because this graph paper is a little bit funky. It's not graph paper that you're used to. So before we start plotting anything, let's just look at the graph paper. So you're used to graph paper looking like having an X grid like this, right? And having a Y grid like this, so that you can count over how many X's and count up how many Y's to be able to plot your points. You're used to that type of a grid. But that's because, of course, the reason why we have this kind of a grid and why we call it rectangular coordinates is because notice that all the grids are rectangles, they're squares, right? And if you plot a particular point, that particular point forms a rectangle. If you think about how far left and right you go and how far up down you go, you get a rectangle. That's why it's called rectangular coordinates. Okay. But that's not the deal here for polar. For polar, again, you start at the pole and you go out from the pole, however that happens to go. Okay. So when we do polar coordinates, anything that's on a circle is all the same distance from the pole. So I'll erase it here in a second, but this circle right here represents all of the points that are 1 unit away. This represents a radius of 1. This circle, if I do this one, represents a radius of 3. So anything that's on that line would be 3 units, or excuse me, anything that's on that circle would be 3 units away from the pole. Anything that's on this circle is 1 unit away from the pole. Okay. So that's why our grid looks like circles rather than lines in this case, is because the farther anything that's on a circle is the same distance away. You think about sticking a pin in at the pole and pulling a string out and then just having a pencil on that string and drawing it around. That's what you're going to get is a circle. Okay, so same idea. So let me erase this now. Let's then talk about the other grid. Okay, so notice that the other way are the angles here, right? And the reason why they're going like this is because your angles start at the pole and are made with the positive x-axis. So this angle would be a 15-degree angle, or pi over 12. The next one's a 30-degree angle, or pi over 6, and so on down the line. So as you rotate around, the angle changes. So all this is doing is putting in a ray, if you will, where each time we have an angle. And it's dividing it up by 15 degrees, or pi over 12. So let's just see if we can recognize where a point is to start with before we start plotting new points. All right, so let me draw. I'm going to keep it red. Why not? Let's say I put the point right here. What are the coordinates of this point? All right. Remember again, for polar coordinates, it's always the r value first and then the theta value. So let's figure out what the r value is. Again, for r, it's the distance from the pole to the point. Okay, that's the r value. Notice that we are on the circle that crosses through 3. So the 3 would be your r coordinate. So this distance would be 3, if I was just worried about distance. Okay. Now what about the angle? Well, again, the polar axis is the positive x-axis. Okay, so drawing that in red, that's your polar axis. And then remember, when we measure angles, if we go up, around, counterclockwise, that's a positive measure. If we go down and around, that's a counterclockwise, that's a negative measure. So in this case, if I go this way, then this angle looks like it's pi over 4, or 45 degrees. But notice that's not the only way I could have measured that angle, right? I could have also measured the angle around this way, right? That's another way to measure that angle. It doesn't have to be positively measured. It could be negatively measured. So another representation of this would have been 3, the r coordinate, but I could have also used negative 7 pi over 4. If I subtract 2 pi from that angle value, I would get negative 7 pi over 4. These 2 points are the same point. Okay? They represent the same point. So notice that polar coordinates are not unique for a given point. In fact, if I do any 2 pi rotation, either in a positive way or a negative way, I end up with the same point. And we've already seen things like that when we solved equations and got all the solutions to an equation, right? We use the 2 pi n at the end. So in particular, if I write down 3, comma, pi over 4 plus 2 pi n, this would represent, all of these represent the same point, the 3 pi over 4 point. Because I can add or subtract as many multiples of 2 pi as I would like, because adding and subtracting a multiple of 2 pi just means that I've gone around the circle one more time. Okay? So we get multiple representations of the same point in polar coordinates. That's different than when we do rectangular coordinates, right? You have an x, you have a y. When you know the x and the y, that's it. There's not, if your x changes, if your x is a different number, it's a different point. If your y is a different number, it's a different point. Okay? The same is not true for polar. You can have different thetas and end up at the same point. You can actually have different r's and end up at the same point, and we'll talk about that here in just a second. Let's see if we can read one more point off of here before we do the plotting of what it's asking us to plot. So let me erase some stuff here. Actually, it's probably just easier to do it this way. There we go. All gone. All right, so let's say I ask you for this point. Yeah, let's make it actually on the line so we can see. Do this point right here. Okay, so we need an r coordinate and a theta coordinate. Theta coordinate is pretty obvious, but we'll talk about that here in a second. Before I'll do the r first. R is distance from the pole to the point. Well, I can just count the grid lines. 1, 2, 3, 4. So the r value is 4. The theta is the angle we make with the positive x-axis. Well, I can see that this one's already labeled for us. This 2 pi over 3 means that we've gone this way around and hit 2 pi over 3. So the angle part would be 2 pi over 3. We could have also done same 4, but we could have measured it this way, subtract 2 pi, and got negative 4 pi over 3. Or we could have gone all the way around one time and then went to it, and that would have been 8 pi over 3, adding 2 pi or 6 pi over 3. And you can do this all day long with adding and subtracting 2 pi. That's what I mentioned before. All right, let's see if we can plot. So instead of me giving you the point and then reading the coordinates off, let's see if we can go the other way. We're given the coordinates, and let's see if we can plot the point. All right. This point, the first point here is 3, 11 pi over 6. Ordinarily, what I do is I will, well, actually we'll do it both ways. Depends on the problem, all right? But usually I count out and then rotate, okay? So this is 3 units, so I need to count out 1, 2, 3, okay? Now that's not the point, I just put the dot there so I can tell you that I counted out to 3 here. Now I need to rotate 11 pi over 6, okay? Well, it's a positive angle, so I need to rotate this way, and I need to stay 3 units out, so I need to stay along the circle until I get to 11 pi over 6, which is over here. So there is where that point is. I'm going to erase this helping line now. So this point here is 3, 11 pi over 6. Okay. We could also recognize, just as the reinforce what we talked about a minute ago, we can also write this as 3, negative pi over 6. Measuring it this way, right? Coming from the positive x-axis and going down, going over the polar axis and going down. That's a negative angle measure. And again, lots of other types of angles, but those are the two more obvious ones that we could do. All right, so let's look at how the second one here differs from the first one. Well, the big difference is that we've got a negative here with my 3. How are we going to handle that when I just told you that r is a distance from the origin? Okay, well, there's two ways to handle it. I'm going to erase some of these arrows off of here so that I not get confused by the arrows as we go around. There's two ways to do this, and this is why I said for me it depends on the problem. So one way to do it is to count your radius first, the r value first, and then rotate. All right. Well, we said 3 units was 1, 2, 3 this way. Well, again, thinking of this as a positive axis, if I went 1, 2, 3 this way, a negative 3 would go 1, 2, 3 this way. Okay. Now, from here, I have not from the positive x-axis anymore. When we've counted backwards, I got to go from here when I do my angle. From here, I need to go positive 11 pi over 6. Positive is counterclockwise. So from this point, I've got to start going this way, and I've got to go 11 pi over 6, which is all the way around over here. So I end up right here. Oops, and I apparently had the dot on it. So here is the point, negative 3, 11 pi over 6. Again, let me go through that again, because I think that the plotting with the negative r values is confusing. And then I'll also talk about how you can think about it the other way. Okay. All right, so first, r value is negative, so instead of going to the right, we went to the left. 1, 2, 3. Angle is 11 pi over 6. I still have to go positive, right? So I don't go this way. That's not a positive angle. This way is positive, counterclockwise, right? We would go around this way, okay? So I have to go this way, 11 pi over 6, not to this label. That's only 5 pi over 6. We haven't even made it a half rotation yet to here. I've got to go from here and go 11 pi over 6, which is almost 2 pi to there. Okay. So again, that's one way to get at it. Let's talk about the other one and make sure that we're at the same point. Okay. The other way to think about it is first, think about your rotation. My rotation was 11 pi over 6, which would mean I would end up on this line, right? End up on this line at 11 pi over 6. Well, positive out from this line would be 1, 2, 3. So instead of going 1, 2, 3 in the positive direction, we would go 1, 2, 3 in the negative direction and end up at the same place. Okay, let me go through that again, just to think about it the other way. Start here and just think about the rotation. The rotation would be here, right? So positive direction's on this line, this direction. So I would go 1, 2, 3 would be positive. So it's negative 1, negative 2, negative 3 for the negative. So that's the other way to think about it. All right, well, let's think about how else we could describe this at this point. Well, first, if I like it with a positive r value, notice I would go 1, 2, 3, positive 3. What's the angle, though? Well, if I went positive 3, that means my angle was this way, and I would get 5 pi over 6. So that's the same representation. So notice that when I have a negative in my r value, if I want to make it positive, I just need to add or subtract pi from that middle part. From the angle part. I have no idea why I said middle part. There's no middle here. To subtract the pi from the angle part here. All right, we're going to practice more of these as we go along. All right, let's look at the next example. Let's plot the first one. I'm going to go through it both ways again like I did the previous one. Let's do backward. This is the pole. Negative 3 goes backward. 1, 2, 3. Now I need to rotate 23 pi over 12. Well, 23 pi over 12. 23 pi over 12 is almost all the way around. And there it went, sorry. Keyboard got locked up when I wanted to try to add some text in here, and I have no idea. why I wanted even to do that. All right, so let's try this again. Negative 3, 23 pi over 12. We went backwards, 1, 2, 3. And now we want to rotate 23 pi over 12. Again, we have to rotate starting going this way, because that's the positive direction from here, right? Don't get confused. Up and around is positive here, but by the time we get to the other side, it's down and around. That's positive. I got to go 23 pi over 12. Well, where is that? Well, an entire rotation is 2 pi, which is 24 pi over 12. So 23 pi over 12 is just short. It's right here. So this would be your negative 23 pi over 12. Again, the other way to think about it would be first, think about rotating 23 pi over 12 first. That would be to here. That's almost all the way to 2 pi. These are, again, in pi over 12 increments, the angle lines, or for 15 degrees. So here's your 23 pi over 12, but instead of counting 1, 2, 3 positive, you're going to go 1, 2, 3 negative, and there's your 23 pi over 12. Again, we notice that we could have described this with a positive 3. And instead of doing 23 pi over 12, we could have used 11 pi over 12. I could subtract pi. If I have a negative making it a positive, I could subtract pi to get the point. Pi is 12 pi over 12, so I can just subtract. Or again, just look where the point is. That's 11 pi over 12, because all the way to here would be 12 pi over 12. Let's do the last one. Negative 2 pi over 3. I'll do it both ways again. Let me do this one in black and erase this green line. Backwards 2. Backwards 2 is this way. 1, 2 to here, right? Right here. And now negative 2 pi over 3. Uh-oh, they throw a negative angle in with this. Well, we just said that down from here is positive, so negative from here must be up this way. And think about it. If I go from the positive x-axis and go down around negative, I'm up when I'm on the opposite side. 2 pi over 3 from here. Well, there's 1 pi over 3 from here. Here's 2 pi over 3 from here. So this is this point. And notice in this case, if I read it off the graph or do our little trick, that's the same thing as 2 and pi over 3. I can just see it from the graph, right? 1, 2 out and rotate pi over 3. Or if I flip the sign on the r, I either add or subtract, doesn't matter which, add or subtract a pi on the angle. If I add pi to negative 2 pi over 3, I get pi over 3. The other way to think of this, I went backwards and then rotated. The other thing would have been to rotate and then go backwards, right? Do that in green here. Rotate would be go this way to there. That's negative 2 pi over 3. Positive from here would be 1, 2. So going backwards would be negative 1, negative 2. And you end up at the same place. All right. So that's plotting. So let's see if we can do the next problem here. What asks us to find all pairs of polar coordinates that have the same point. All right. So one of the things that we said was, one of the things that we can do is we can always add or subtract multiples of 2 pi and end up the same place. 2 pi represents an entire rotation. So I can always add or subtract the 2 pi and get another representation of the point, right? So we see that right up here from the problem we did before, correct? Instead of doing 11 pi over 6, we could have done negative pi over 6. That's subtracting 2 pi from 11 pi over 6. The other thing we said was, if we flip the sign on the r, we can add or subtract a pi to the angle. Okay? So I could do 5 pi over 6 plus pi or minus pi, doesn't matter. You can add or subtract. Either way works. Because again, if I add pi or subtract pi, that's only a 2 pi difference. So remember, 2 pi doesn't change anything. That's just a rotation. So this would be negative 1 and then 6 pi over 6 plus 5 pi over 6 is 11 pi over 6. And now, just like this previous one, we could do -1 and then 11 pi over 6, and I could add multiples of pi, or 2 pi to that all day long and get the representation. So here's all representations of that point. I can either just take the original point and add multiples of 2 pi to the angle, or we can negate the r value, adjust the angle by adding or subtracting a pi, and then adding or subtracting multiples of 2 pi. So let's do the second one here. One is very straightforward. I can add or subtract multiples of 2 pi. Again, 2 pi represents a complete rotation. So if I add a 2 pi, or I subtract a 2 pi, or I add a 4 pi, or subtract a 4 pi, doesn't change where the point is, because all I've done is just go in a circle all the way around. The other way, again, is to negate the r value. Either add or subtract pi to the angle you start with. If I subtract pi here, I will get -pi/12. Again, does not matter if you add or subtract. You can do either, add or subtract a pi. You'll end up with the same answer. And then add your multiples of 2 pi. So these would be all your representations of the point. Okay, so we've emphasized that polar coordinates can have multiple representations. So now let's let's practice with doing some conversions. We'll stop after doing some conversions here, and then we will talk about doing conversions of equations like we see down here on the next page. We'll talk about that in the next lecture for Monday. All right. This one asks you to convert from polar to rectangular. Converting from polar to rectangular is a very straightforward exercise, I promise, okay? We already had those formulas that we know that x is equal to r cosine theta and y is equal to r sine theta, okay? So notice that if we know the r and we know the theta, we automatically know the x and the y. Without any doubt, right? Without any question, we know the x, we know the y. So these, like I said, these are very, very straightforward, because if these are polar coordinates, the first coordinate's the r, the second coordinate's the theta. So to convert this to x and y, we just need to plug in the r and plug in the theta. Okay? So this one, your r is going to be 2 times cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0, so your x is 0. Your y is 2 sine of 3 pi over 2. Sine of 3 pi over 2 is -1, so you get... And so your point is -2. Let's see this from the graph. Let's do this from a graph. I'm going to go scroll back up and grab some of this polar graph paper so I don't have to find it somewhere else. Let's go over here. Okay. The point was 3 pi over 2. Okay. So again, if I count over 2 in the positive direction and then rotate 3 pi over 2, I end up right here. Now, pretend like the circle grid's not here. Pretend like this is your x-axis and your y-axis as usual. What's your x-coordinate? Oh, it's 0, because my point is on the y-axis. What's the y-coordinate? Oh, it's -2, because I'm down 2 from the x-axis. So I see quickly that the coordinates of this point really are 0, 2, -2 in rectangular coordinates. Okay. All right. So let's do the next one. Again, straightforward. X equals 1 cosine of 5 pi over 6. Cosine of 5 pi over 6 is -√3 over 2. So your x is -√3 over 2. Y is 1 sine of 5 pi over 6. Sine of 5 pi over 6 is 1/2. So the coordinates are negative root 3 over 2 and 1/2. All right, last one here. Even though this doesn't have a pi in it, we do it the exact same way. X equals negative 3.2 cosine of 5.8. Now, in these problems, when you're doing these, make sure your calculator is set back in radians. You've probably had your calculator set in degrees for the last couple of sections because we've been solving triangles and finding areas. So make sure your calculator is in radians for this, making sure it's out of degree mode and in radian mode. Because we're going to round these to some decimal places. So in this case, I want to take the negative 3.2 and multiply by the cosine of 5.8, and we get, looks like, negative 2.8337. Your y will be negative 3.2 sine of 5.8. So do that and get what here? It's about 1.4867. So your coordinates will be negative 2.8337 and 1.4867. Again, converting from polar to rectangular, pretty straightforward, right? Just got to plug the points in. You got to plug the r value in, plug the theta value in, and you're done. That gives you your x and your y. Converting from rectangular to polar is almost as easy, but we have to pay attention to a couple of things. One, the directions like to ask you to make sure your theta is in between 0 and 2 pi. We want to make sure that we have a positive theta and we haven't gone more than a full rotation around to get to where the point is. So that's one thing we need to pay attention to. Another one, it also says make sure that our r is greater than 0. That one's not hard because we either are going to have a positive r or a negative r. We'll just make sure we always use the positive. The other part that's going to pop up that's tricky is we actually have to pay attention to what quadrant the point is that we're dealing with. And we'll see that as we go along. That's why I've got 6 of these and only 3 of the previous ones. These are a little bit more, well, a little trickier. All right, so again, this is your x, this is your y, and we want to find an r and find a theta. Okay, so r is easy. The theta is the one that's the trickier one. I promise the r is easy. Okay, r squared equals x squared plus y squared. Pythagorean theorem, you've been doing Pythagorean theorem ever since you learned Pythagorean theorem, probably back in middle school. Okay, so your x is 3 root 3 over 2. Your y is 3 over 2. 3 squared is 9. Root 3 squared is 3. 9 times 3 is 27. So this is 27 over 4. And this is 9 over 4. So you get 36 over 4, or 9. Simplify. R is 3. We don't need to worry about the plus or minus here, because in particular because the problem says use r greater than 0. So I don't use the minus part. I just use the plus part. Okay. R is always this straightforward, especially when it asks you for an r greater than 0. Converting from x, y to r, you're just going to use r squared equals x squared plus y squared. It's always this straightforward. Okay. It's the theta that requires a little bit more work. Okay, so the other conversion that we have is the tangent of theta is y over x. Okay, well, the y is 3 halves, and the x is 3 root 3 over 2. So when you simplify, you get 1 over the square root of 3. Okay, we like exact values if we can find them. This one's not too bad. We see that theta must be pi over 3. That's the angle that's in the first quadrant, but we also know that there's an angle in the third quadrant that would have the same tangent value, right? Tangent is positive in 1 and 3. So we have to make certain that the answer we're getting from our tangent makes sense with the point that we're dealing with. Well, since the x is positive and the y is positive, we're in quadrant 1, and pi over 3 also has an angle in quadrant 1, so we're good. So the coordinates of your point will be 3 comma pi over 3. Okay, let's do the next one. The r, again, straightforward. R squared equals x squared plus y squared. R squared is negative root 2 squared plus root 2 squared. 2 plus 2 gives you 4, so your r is 2. Again, r is not the challenging part of this. R is just the square root of x squared plus y squared. Especially since, again, like I said, it's asking for the r value to be positive here. So, all right, tangent. So we'll have y over x. Y is negative root 2. X is root 2. Not root x, root 2. So we get negative 1 when we simplify. Okay, so again, we like exact values when we can get them. We might have to use our calculator on occasion, but in this case we can find it. All right, first off, if I ignore the negative, I know that tangent equals 1 when we're talking about a pi over 4 angle. Okay, I also know here that the tangent is negative. Tangent is negative in quadrant either 2 or 4, right? Quadrant 2 or quadrant 4. All right, well, let's look. Now I got to look at the point. The point has a negative x value, a negative x, and a positive y. Negative x is this way, positive y is this way. Your point is over here in quadrant 2. So the pi over 4 angle that lives over in quadrant 2 is 3 pi over 4. So our point in this case is 2 comma 3 pi over 4. All right, let's do the next one. R squared is x squared plus y squared. R squared is negative 3 squared plus 0 squared. So r squared is 9, r is 3. Again, the positive r, even though we started with a negative 3 in there, the r is 3. Okay. All right, this one, we can do the theta. Tangent of theta is y over x. Y is 0. X is negative 3, so we get 0. When is tangent equal to 0? Well, tangent is equal to sine over cosine. So the tangent is 0 when the sine is 0, which happens at 0, pi, 2 pi, and so on. Well, in this case, where is this one? All right, again, I think this one's just as easy to go to just look at where the point is. The original point is, this is rectangular coordinates, negative 3 comma 0. That's right here. Well, what angle is this? Well, it looks like theta better be pi. Okay, so we get the point 3 pi. I think that one's just as easy to plot the rectangular point and see where the angle is. Only 3 more to go here. We'll get there. Again, R not the hard part of these problems. Just plug it in and go to town. Get R equals 2. All right. We could go. I'm going to go through the formula for theta here in a second, but let's just think about where this point is. 0, negative 2. X is 0, y is negative 2, so we're down here. This angle going around this way must be 3 pi over 2. We see that. Because again, going from the positive x-axis and making a positive angle, right? Got to rotate that way. What would we have seen had we tried the formula? Tangent of theta equals y over x. Theta is negative 2, x is 0. Uh-oh, we've got a 0 in the denominator. That means this is undefined. Where is tangent undefined? Well, if we think to the graph of tangent, we've got those asymptotes. That happens when the cosine is equal to 0. So that must mean we're at pi over 2 or 3 pi over 2. I'm going to have to go back to the graph, or where the plot of the point was anyway, to figure out where that 3 pi over 2 is. So going through this part, wasn't exceptionally helpful for us because I was going to have to go try to figure out, am I at pi over 2 or I'm at 3 pi over 2 anyway. So in that case, it probably was just as easy to plot the point to start with. All right, 2 more. Again, very straightforward to get your r. You get r squared equals 13 in this case. So r is equal to root 13. Theta is more difficult. Tangent of theta equals negative 2 over 3. Right? That's y over x. Okay, so I don't know that one, so I need to do the inverse tangent of the negative 2/3. If I put in my calculator, put in 2/3, make sure I make it negative, do the inverse tangent, that tells me my theta is approximately negative 0.5880. All right, well, I already see I have an issue with this because the problem asks us to find theta between 0 and 2 pi. This is not between 0 and 2 pi. All right, so what do I need to do to this value to make it between 0 and 2 pi and give me the point I want? Well, first off, I know that my theta is negative, or my tangent of theta is negative, I should say. So that means I'm in quadrant 2 or quadrant 4. This point, 3, negative 2, is in quadrant 4. All right, so what do I need? This already is in quadrant 4. This is our negative 0.588. I need to go around this way. So our theta really needs to be 2 pi minus 0.5880. So our coordinates here, and I'm going to leave it in a funky form. You could, Hawks probably will want you to put it in your calculator to get decimal points or decimals approximations for both of those. But for me, you can leave it like this. This is perfectly fine. This tells me you understand how to find the point. All right, last one. R squared equals negative 5.5 squared plus negative 8.9 squared. 5.5 squared is 30.25. And 8.9 squared, oops, I hit the wrong button. 8.9 squared is 79.21. So add that to the 30.25. We get r squared is 109.46. Need to take the square root of both sides. That one's not going to be a pretty good approximation. 10.4623 for your r value. I know I went quickly through the r, but it literally is just a matter of plug in the x, plug in the y, find the r. I spend more time on the tangent because it's the harder one. At least I think it's the harder one. All right, so tangent of theta is y over x. Y is negative 8.9. X is negative 5.5. That's not one of those angles that I know the tangent of. So I need to put this in my calculator. Notice that the negatives go away. Makes our inside fraction positive. So I'll do the 8.9 and divide it by the 5.5 and do the inverse tangent of it. And I get approximately 1.0173. Okay, now again, this is where it comes a little trickier because I have to be careful. Remember, when I do the inverse tangent, it always gives me an angle in quadrant 1 or quadrant 4. This point most definitely is not in quadrant 1 or 4. That point is in quadrant 3. So to get this angle to be over in quadrant 3 instead of in quadrant 1, we need to add pi to it. So there's our polar coordinate representation at that point. Okay, so I've posted a whole bunch of practice problems on Moodle as well for these. we're going to talk about the second half of this lecture on Monday. So you can start going through some of those practice problems if you want some extra practice with this. There are ones just like this, but if you're getting to the ones that look like it is asking you to convert an equation from rectangular to polar, hold off on those over the weekend. We'll talk about those on Monday. All right, everybody have a good weekend.